Okay, so thank you very much for inviting me here. I'm happy to talk here because now I've been away from ocean and let's say atmospheric data assimilation for quite many years, working in more in reservoir applications, and but now I also and more doing parameter estimation than proper data assimilation. But I see that the methods we are using have a lot in common, and in the end, they can actually be framed into the same equations. So we are basically solving the same problems. This talk is about iterative methods and iterative smoothers, and which has become really popular in the reservoir community. And there's also a parallel development of iterative smoothers in also for atmospheric data assimilation with Mark Bouquet and Pavel Sakov and these groups. And but there has been a kind of two parallel developments in the reservoir community. It's mostly stochastic ensemble smoothers, while the square root formulations has been developed more by Mark and Pavel. So in this talk, I will talk mostly about the stochastic versions. In the end, it turns out that they all converge more or less to the same thing, as long as you have sufficient number of realizations, so it's not so important. But I think the main message in this presentation is that iterative methods will give you a much better improvement of the results than any other or changes you will do to your schemes if you choose stochastic versus square root methods, or you try to make small adjustment to your schemes. But this concept of introducing iterations increases the computational cost, but it really improves the results, and it kind of handles nonlinearities quite well. So just to show you what I've been working on for the last few years. It's more these reservoir models. This is a subsurface structure, so it is several hundred meters below the ground. And you have accumulation of oils that are trapped within, there's a sealing surface on top of this, and underneath you will have gas and or hydrocarbons. And then you put this into a numerical model. So you have, you try to characterize all the rock properties like porosities, permeabilities, you have faults, you have fault multipliers, you have a kind of numerical representation of your reservoir. Then you start drilling wells. So you have these red ones, which are injectors. There you can inject water to increase the pressure in the reservoir. Then you have all these producers where oil and gas is flowing out of the reservoir. The problem with this is that you have very little measurements when you define the model. You have some seismic data that gives you, within some uncertainty, the location of the different surfaces of the top reservoir, the bottom reservoir, and the kind of intermittent surfaces in the reservoir. And then you have measurements from the point measurements from the wells, where you take out cores and you look at the rock properties, and you based on this, you're using geostatistical methods to describe or characterize the whole reservoir. But then when you start producing, you realize that what you inject and what comes out of the wells is not what you see in your model. So the model is wrong. And that means you have to, you will try to improve your model, and you do that by changing the rock properties and all these different coefficients. And typically you can think of, suppose you inject water here, then you increase the pressure between this injector and the producer. So more oil and gas will stream from the injector to the producer. And if there's too little oil coming out, then you can imagine that we should increase the permeabilities or porosities between the injector and producer. And that's what you are doing with parameter estimation. And now we have methods that are extremely flexible. We can update these full 3D fields of rock properties. We can even update the model grid, the model definition itself. So we can have realizations of these models located at slightly different depths, with different thicknesses, etc. And this is possible using ensemble methods. And then this is just one example using a standard ensemble smoother. And here you have these blue curves, which is this is oil production rate, gas, water here. We have the measurements in black. The blue are the priors. The red is the, just one second, updated ones. And you see here that you are reducing the uncertainty, but still it's quite a large uncertainty in the posterior estimate as well. But anyway, so this is the accumulated versions of these. And yeah, so the Ensemble Smoother was kind of successful, but these models are still quite nonlinear in a way. And when we introduced iterations, we would get something like this. And so this is an iterative smoother. So here you are doing some iterations, and you see that you get a much lower uncertainty in the posterior estimates. You know you have multiple realizations that are fitting the data quite well. And the only data you have used here are these production rates. So this is just to say that as soon as we started developing iterative methods, we got a big improvement in the results. Now I'm going to show some equations. Actually, there will be lots of equations in this talk, but I will start with some simple ones. This is the way we define the problem in a kind of generic form for this history matching problem or parameter estimation problem. In X, we put all the uncertain parameters. And these are all static parameters, right? So it's a huge vector with 10 to the power 6 unknowns in this one. Then we have a nonlinear model, which leads to a prediction Y. And the prediction is now the oil coming out of the wells. Okay? Then we are measuring what comes out. We have big uncertainties in these measurements, but still we have measurements of the produced oil. And if we cast this into a Bayesian formulation, we have a prior for all of our geostatistical parameters. We have a model that model transition density that gives us the prediction, and we have the likelihood PDF for the measurements. And then the posterior of the parameters and the prediction given the data is proportional to this. And this is the kind of the starting point when we derive these methods. Now if you look at this alternative formulation, now we are looking at data assimilation, so there's no parameter estimation anymore. So now we have a prediction of the state vector, so this could be the pressures, velocities, etc. We have a nonlinear measurement operator that gives us the data. Okay, so we measure these Y's here, the predictions. And again, we can write exactly the same Bayesian formulation for this problem. We have the prediction, we have the measurement operator, we have the measurements, and we get this posterior. So that means these two formulations are essentially the same. It's just different inputs and models. Okay, if we go one more step now, suppose we have a forward model. We write it like this, so M is our forward model. We have the solution at the previous time, and we make a prediction at xi plus 1. Again, we have the measurement, nonlinear measurement operator of this prediction. So we can write it like this. And again, we get back this y equals g of x. And we measure y. And we get exactly the same equation again. So this would be what we call a smoother update step. Okay, and it's an indirect update. We update the solution at the previous time, and then we integrate the model to get the updated prediction. In this formulation, there are no parameters, so we can add parameters as well. So now we have the previous solution at the previous time, and we have static parameters. We call them alpha now. We put all of these into one x tilde here. And again, we get exactly the same formulation. So we can formulate the combined parameter and state estimation in exactly the same way. And if we want to go really crazy, we can add model errors. So these Q's are now uncertainties in the model, uncertainties in numerics or model formulations, etc., that are neglected. And again, we put everything, lump it into one x. And we get exactly the same equation again. Y equals a nonlinear function of these inputs. And we have the base Bayesian solution here. And again, we can solve this, and we find estimates of x at the previous time, the parameters, the model errors, and we insert them here and make the updated prediction. Okay. We are not really interested in estimating y. We won't estimate these parameters in here, or the x. So we compute the marginal of this one. We integrate over y. And with this formulation of the model PDF is just a delta function, like this. Okay? Because model errors, everything are now included within the g of x. And if we integrate over y, we get the marginal PDF. So this is the PDF of x given the data is proportional to the prior times this likelihood function, and here we have the nonlinear model coming in. So this is what we will solve. And by showing these equations, I've kind of explained that parameter estimation, state estimation, indirect updates in state estimation can all be formulated into the same sort of equations and handled the same way, basically. So there's no real difference of that in those. Okay, this posterior PDF here, we want to maximize it or sample it, or depending on the method you use. But what we normally will do is to assume that these priors are Gaussian. And if they are Gaussian, we can write a standard cost function like this. And then we know that in the case when we have a linear model, then we have an exact solution of this one, which is the Kalman filter update. And this can be written in an ensemble form, ensemble representation. And when the number of realization goes to infinity, it exactly matches what you get from the standard Kalman filter. And it's also interesting to see that this equation, the ensemble equations, can be derived from an ensemble of cost functions. So you have one cost function for each realization. So we have the different prior realizations here and the different perturbed measurements here. So that means in the linear case, these are all the same. Okay? And we can derive ENKF and, in fact, all these other methods from this cost function here. In the nonlinear case, it's a problem because then solving, minimizing this ensemble of cost functions does not exactly sample the posterior. It's an approximation to the posterior. But still, all the methods we are currently using today are dealing with this kind of minimization problem. The square root methods are a bit different because they would minimize. They would try to find minimize this one, and then they assume a Gaussian posterior. So that means you find the best estimate of the mean, and then you generate perturbations which are Gaussian around that mean for the posterior. But I'm not going to talk more about that. Okay, since this is an atmospheric data simulation workshop, you are used to work with tons of unknowns and data and very few realizations. So here I'm turning everything upside down. I will have a model where the state dimension is 1 and have one measurement, and then I have 10 million realizations. And the reason for doing that is that I can create this nonlinear scalar model, and I can look at PDFs coming out of the different methods. Okay, so I know something about the limiting or what I would expect to get using different methods, and I eliminate sampling errors. And I will look at linear models where this beta is 0, and nonlinear models where beta is 0.2 in this case. And just to recap a bit from what I started with this morning. Suppose this is my prediction y. And now I have a nonlinear model, so the predicted PDF is non-Gaussian. It has a long fat tail here. And then I have a likelihood function for the measurements, this green one. And the theoretical posterior for base is this black line. It looks a bit Gaussian, but it's not entirely Gaussian. It's a bit asymmetric. If I do the standard ENKF update, so then I I'll come back to that. But then I get an estimate, which is this dashed line here, which is quite far from the posterior, okay, or the theoretical solution. And the reason it's not exactly the theoretical solution is that you have non-Gaussian ensemble as the input. So you are making approximations, okay? In fact, what you do is to represent this one with a Gaussian. If you compute the indirect update, so then I have a prediction model here. I update xj at the previous time, and then I recompute the prediction. Then my PDF looks like this. I get this dashed or thick full blue line here. And in this case, it actually looks better than the direct update. And what you can deduct from that is that this indirect update might reduce impacts of non-Gaussianity. But the important thing is that this formulation actually allows for iterative methods, deriving iterative methods. So, okay, so now I will move more into that. And some of the results is from a paper that was published last year, which is showing all these scalar examples with the two different iterative smoothers. And I'm going to present two different iterative methods. One is called ESMDA, which is Ensemble Smoother with Multiple Data Assimilation. And the other one, I call it Iterative Ensemble Smoother, but it's also called Ensemble Randomized Maximum Likelihood, ENRML. The reason I'm choosing these two is that they are fundamentally different in their formulation. And I will spend a little bit of time trying to show or explain the differences between them and try to see what they actually are solving. So, okay, all these methods are derived from this ensemble of cost functions. And I wrote it in a scalar form now, so I have no matrices. It makes it quite easy to see what's happening. You compute the gradient of this one, so it's just a derivative with respect to x. And you can compute the Hessian, which is the second double derivative. And normally this term is neglected. Thank you. If you look at the three different methods, the ensemble smoother, what it does is to set the gradient equal to 0. You set this equation equal to 0, and you solve for xja, the analysis. And to be able to find an explicit equation for the solution, you have to linearize, in particular, this term here. So you linearize your model around the prior. And then you get this equation here. So now you have an explicit solution, but still you have your derivatives of your model in here. So you have the tangent linear model involved still. So in most applications, you cannot solve this because you would need an adjoint or you need to compute estimates of the derivatives of the model. However, in the ensemble methods, we replace these terms with using linear regression or kind of least square fit to this. So, and also interesting here is that you have different equations or different gradients, whatever, for each realization. So when you go to an ensemble method, you replace this term with one common gradient. So all the realizations will use the same gradient term. And it's based on linear regression. Interesting is that with my simple scalar model, I actually know I can compute these derivatives. So I can compare the analytic and the ensemble formulation of the method. I can see what the impact of this approximation is. And it has an impact. Yeah. So basically, in the ensemble smoother, you go one long step based on a linearization around the prior. And you can expect that if the model is quite nonlinear, then the direction you have here is not necessarily very good. ESMDA is trying to use the same ensemble Kaplan filter equations, but instead of going one long step, it wants to split up this step into several smaller steps. And the way it's doing it is by something called tempering of the likelihood. So you write the likelihood as to the power of 1, and 1 is just this sum over 1 over alpha. And that means you can write it as a recursion or a multiplication of several likelihoods. And then you can process these ones recursively. And in a Gaussian likelihood, you get this 1 over alpha in front of the quadratic term. And if you look at the equations, you have this alpha I in here, and you have the square root of alpha in here. So basically, you can use the same equations as you have in your standard ensemble gamma filter, but you just scale the measurements and the measurement error covariance, and and solve it multiple times. And for example, if you want to do 2 steps, then alpha would be 2. So you have 2 times CD here and square root of 2 in here. And you just do it twice. And theoretically, in the linear case, it will converge exactly to the posterior base. So in this case, we are doing multiple short linear steps in kind of an average direction, so the same direction for all the realizations. Yeah, the iterative ensemble smoothers are using a Gauss-Newton method to minimize the cost function. So that means they put a gradient in the on top here and the Hessian below, and you do as many steps as you like until convergence. So it's a standard gradient method. Obviously, you get a different result. They will not converge to the same thing, but it's The nice thing is that this formulation here, when you still have the analytic gradient, will exactly solve the cost functions you specified. There are no approximations. You find the exact solution. It's just unfortunate that the solution is not exactly sampling the posterior. But and then we can do some tricks. We're again with linear regression, and we get everything set up using an ensemble representation. So you get rid of the model, and that's the beauty of ensemble methods. You get rid of these tangent linear operators, and you get something that you can solve quite easily. Yeah, this is just for the linear case, and I'm showing all the methods in here, and they all converge exactly to the same solution. And then I also show the steps using this ESMDA. And okay, so what I have now is X in this plot. I have the PDF of X. I start with this red one. I make a prediction, so I get this one. Then I combine it with the likelihood to get an update. And with the ensemble smoother, I go directly to the posterior, the blue curve, and then I make a new prediction. With the ESMDA, I will get the first of these PDFs and make a new prediction, combine it again, and it goes gradually towards the theoretical solution. So in the linear case, this is perfect. All the methods give exactly the same result. In the nonlinear case, they all give us different results. This is again the ensemble smoothers. It's the same as I showed you before. You start with X, make a prediction, combine it with the likelihood. You get this dark blue curve if you use the analytic formulation, and you get the cyan curve if you use the ensemble formulation. So you see that there's quite a big difference, or quite a big impact of going from the analytic or adjoint formulation to the ensemble representation.